Hi everyone, this is Praneetha and this presentation is all about asymptotic notations and their analysis. So let's get started. The basic questions that arises are why, what and when to use this asymptotic notations. So coming to the first question, what are asymptotic notations? If we consider any algorithm which will be having a sequence of steps, of those steps, some of those steps will be the basic operations, and number of times we perform those basic operations or we encounter with them will be the count of that particular algorithm, and this count is nothing but the time efficiency or the running time of that particular algorithm, and this time efficiency is described in terms of asymptotic notations. So basically we use asymptotic notations when we have to find the time complexity of any algorithm, and so we can define the asymptotic notations as the functions whose domains are the set of natural numbers including 0. Such notations are convenient for describing the worst case running time of any running time function if we consider it's t of n. So it can also be extended to the domain of real numbers. Generally, the running time of an algorithm typically grows with the input size. Average case time is often difficult to determine. So we focus on the worst case running time since it's easier to analyze and crucial to the applications such as gaming, finance and robotics. So coming to the denotions of these asymptotic notations, there are basically 5 denotions, that is big-theta, BigO, BigOmega, small o and SmallOmega, and these asymptotic notations are defined over the functions or over the natural numbers. So if we consider an example, f of n equals to theta of n square, here we are describing how my function f of n grows with respect to n square. So these are nothing but the set of functions in practice used to compare two function sizes. These notations describe different rate of growth relations between the defining function and the defined set of functions. So generally, to compare two algorithms with running times, if we consider f of n and g of n, we need a rough measure that characterizes how fast each function grows, which is nothing but the running time of that particular algorithm. So we'll start with the big-theta notation. So if we consider a function g of n, which can be defined in terms of a function f of n, such that there exist positive constants c1, c2 and n0 satisfying all these conditions. So if we plot a graph for all these functions, the functions f of n and g of n, it will be like, as the time proceeds, both the functions f of n and g of n grows rapidly. So intuitively we can say that f of n is nothing but the set of all functions that have the same rate of growth as g of n. As we can see here, the f of n is bounded asymptotically tight by the function g of n. So we can state that g of n is an asymptotically tight bound of f of n. Technically, f of n is belongs to the function g of n, since we keep lying in the range of constant c2 multiplied by gn and c1 multiplied by g of n. So but older usage was that they used to consider f of n equals to big theta of g of n, where both f of n and g of n are non-negative for large values of n. So let us consider an example. Here f of n equals to n by 100 plus 100 and g of n equals to n. So finding out the values of c1, c2 and n0. So satisfying these conditions, let us consider c1 which will be multiplied by g of n will be always in this range. So by calculating these values, let's consider n equals to as well as n0 equals to 1. So we'll be landing up with these values c1 and c2. So if we choose the c1 and c2 values in this range, then the above equation will hold good for any values any values of n which is greater than or equals to 1. Moving on to the big O notation, similarly let us consider a function g of n which we want to define in terms of another function f of n, such that there exists a positive constant c and n naught satisfying these conditions. So once again, if we'll plot a graph for f of n and g of n, it will be like, as the time proceeds, the function g of n grows rapidly when compared to the f of n. So intuitively we can state that set of all functions whose rate of growth is same as or lower than that of g of n, since we can see that g of n is acting like asymptotical upper bound to the function f of n. So it's practically the asymptotic upper bound. So we can also write, since we have proved in the previous slides, f of n is equals to big theta of g of n, which implies f of n equals to big O of g of n. So from these statements we can state that big theta of g of n is subset of big O of g of n. So we'll solve some examples based on this big O notations satisfying these. So any linear function which is in the form of ax plus by and its worst case time complexity will be big O of n square. So if we consider big O of g of n, which is a set of functions with smaller or same order of growth as g of n. So here are some examples. So big O of n will be the time complexity of these functions. Examples for this time complexity. So moving on to examples, some more examples. So here f of n equals to 2n square and g of n equals to n cube. So now we are describing how the function f of n grows with respect to or in comparison with g of n, that is n cube. So putting these f of n and g of n functions in the previous condition, then we'll be ending up with values of c equals to 1 and n naught equals to 2. So similarly, if we prove some more examples, this is for time complexity big O of n cube, and this is for big O of n square, and this is for big O of n square again, and once again big O of n square. And here we are comparing how 2n square grows in on comparing with n cube, and here how n square grows on comparison with n square, and how this function grows on comparison with n square. Similarly the last example. So moving on to the big omega notation. So once again we'll consider a function g of n, and we'll express this function in terms of other functions, let us say f of n. So there exists some positive constants c and n naught such that satisfying these conditions. So if we'll plot a graph for functions f of n and g of n, here we can see function f of n grows rapidly when compared to the function g of n. So intuitively we can say that set of all functions whose rate of growth is same as or higher than that of the g of n. Here we can see that g of n is acting like a lower bound for the function f of n. So we can say that g of n is an asymptotic lower bound of f of n. So similarly by equating the previous statements, we'll be landing with big theta of g of n is subset of big omega of g of n. So let's solve some examples. So here f of n equals to 5n square and g of n equals to n. Once again, if we'll put these functions in the given condition, then we'll be ending up with the values of c equals to 1 and n naught equals to 1. So similarly, all these examples are nothing but how we'll compare the time complexities of any two functions on comparing how rapidly those functions grows. So that's all, and here I'm comparing how 10 and 100 and plus 5, which is okay. This is contradiction. So if we consider this function, so there exists C and N naught such that satisfying these equations, but finally since N is positive, we'll get N value as this. So if we'll consider, and there will be a contradiction statement, as N cannot be smaller than a constant. So here it violates the rule, and there are some exceptions. Moving on to the relation. So there is a theorem which states the relation between the big theta, big omega and big O notations. So the theorem states for any two functions f of n and g of n, f of n will be equals to big theta of g of n if and only if f of n equals to big O of g of n and f of n equals to big omega of g of n, which is nothing but the intersection of big O of g of n and big omega of g of n, which will be leading to the big theta of g of n. In practice, asymptotically tight bounds are obtained from the asymptotic upper and the lower bounds. So if pictorially, if we'll see them, if we consider let us describe them in terms of a Venn diagram. So let us consider this as big O of g of n, this is considered as big omega of g of n, and the intersection part will be but big theta of g of n. So we can even make it from the graph. This is the graph for big theta of g of n, and which is obtained from the intersection of both these graphs. So as simple as that, this is a clear-cut picture for the theorem stated. So coming to the asymptotic growth rate, this is nothing but a way of comparing the functions that ignores constant factors and small input sizes. So if we consider big O of g of n, the class of functions f of n that grow no faster than g of n, as we have seen previously in the when we plotted the graph for f of n and g of n, the way they grow with respect to the time. So that's what here it's been stated. And coming to the big theta of g of n, the class of functions f of n that grow at the same rate as g of n, since as the time proceeds, both the functions f of n and g of n grows rapidly, I mean equally. Coming to the big omega of g of n, which is a class of functions f of n that grows at least as fast as g of n, implies the function g of n will be acting like a lower bound, asymptotic lower bound to the function f of n. And next question is, when we'll use these notations, at what particular instant of time, which notation we have to consider. So coming to the BigO notation, we use the BigO notation when we have only an asymptotic upper bound. Instance, okay, note that big theta of g of n is subset of big O of g of n, since we have proved this. So let us consider an example, n equals to big O of n square. Here f of n is n and g of n is n square. Since big O notation describes an upper bound, when we use it to bound the worst case running time of an algorithm, we have it bound on every input. For example, the big O of n square bound on the insertion sort also applies to its running time on every input. However, big theta of n square on the insertion sort would only apply to the worst case input. So this is when we'll use the big O notation. And coming to the big omega notation, we use this when we are provided with a asymptotic lower bound. If we consider n of any given function, since big O notations describes a lower bound, it is useful when applied to the best case running times of algorithms. For example, let us consider the scenario of insertion sort, and the best case running time of insertion sort is big omega of n, which implies the running time of insertion sort is big omega of n. And coming to the small O notation, which is similar to the big O notation, but this is not asymptotically tight. It's just an upper bound. This notation is used to denote an upper bound that is not asymptotically tight. So similar conditions will be applied. So we are defining the function g of n in terms of f of n, where there exists a constant c which satisfies these conditions, and let's consider an example. 2n equals to BigO of n square. Here f of n is 2n and g of n is n square. So intuitively, if we'll find out the limit of the functions f of n divided by g of n, which will be leading to 0. So this is the basic condition that satisfies the small O notations. And coming to the small omega notation, this is also not completely different from the big omega notations, but simply in this case also it's not asymptotically tight. We use small omega notations to denote a lower bound that is not asymptotically tight. So if you want to express small omega of any function in terms of another function, let us consider f of n. So there exists a constant and satisfying all these conditions. So once again, let's consider an example: n square by 2 equals to omega of n, where n square by 2 is function f of n and n is the function g of n. So if we'll find out the limit of function f of n divided by g of n, which will be leading to infinity. So this will be the basic condition. And coming to the common orders of magnitude, generally if we want to express any function in terms of other function, we'll express in terms of either logarithmic functions n log n square, n cube and 2 power n and n. So these are the basic notations. So these are for the execution times for algorithms with given time complexities. Thank you.